to this in-depth explanation of a groundbreaking research paper titled, Horizontal Homing Laser for High Repetitive Inertial Fusion. This study represents a critical step toward achieving commercial laser inertial fusion energy, a key technology for sustainable energy production. In today's video, we'll explore the problem the researchers are addressing, the experimental setup, their key results, and the implications of this work for future fusion energy systems. Fusion energy holds the promise of providing a nearly limitless source of clean energy. One major milestone toward this goal was achieved by the National Ignition Facility, which demonstrated fusion breakeven through single shots. However, moving from single-shot experiments to a practical, commercial fusion reactor requires the ability to operate continuously and repetitively, at rates of 10 Hz or more. This means fusion reactors must be able to inject, track, and engage fuel pellets at incredibly high speeds and with extreme precision. To achieve this, researchers must overcome a series of challenges. A primary one is controlling laser pointing to ensure it aligns perfectly with fuel pellets that are injected at high speeds. Small fluctuations in pellet position can lead to misalignment, drastically reducing the success rate of fusion events. In this paper, the researchers aim to solve the problem of laser alignment by demonstrating a laser pointing control system that tracks and engages free-falling fuel pellets with a high degree of accuracy. Their specific goal was to achieve this at a repetition rate of 10 Hz, which is a key requirement for the commercialization of inertial fusion energy. The experiment was carried out using a disc-type free-fall injector, which released stainless steel balls of 1 mm in diameter. These balls served as test pellets, simulating the behavior of fuel pellets in a fusion reactor. The pellets were released at a repetition rate of 10 Hz, and their positions were tracked using an array of sensors. The laser system used in this experiment operated at a wavelength of 1053 nm with a beam spot size of 1.6 mm. The key component of the system is the galvo mirror, which adjusts the laser's beam position based on data from tracking sensors. The goal was to cancel out any horizontal fluctuations in pellet position, ensuring that the laser hit its target with an accuracy that is sufficient for successful fusion reactions. The experiment yielded promising results. The researchers were able to demonstrate precise control of laser pointing, achieving a success rate of 92% within a 0.15 mm difference between the laser spot and the center of the fuel pellets. This level of precision is sufficient for enabling nuclear fusion under the conditions set at the Hamamatsu facility. They demonstrated that the horizontal fluctuation of the free-falling pellets was significantly reduced, with a standard deviation of only 86 micrometers. This is a critical step forward, as minimizing such fluctuations directly increases the likelihood of successful fusion events. However, there are still areas for improvement. While the horizontal tracking system performed well, there were some challenges with vertical synchronization due to the effects of air resistance. The authors note that their system, which operated in air, would likely perform even better under vacuum conditions, similar to those in an actual fusion reactor environment. Furthermore, the system needs to be scaled up for commercial application. This includes upgrading the galvo mirrors and sensors to handle higher speeds and larger mirrors, which will be necessary in future fusion reactors. This research is an important proof of concept for the homing laser system in fusion reactors. If successfully integrated into commercial-scale reactors, this technology could dramatically increase the efficiency and success rate of inertial fusion energy systems. The research team has already outlined steps for improving the system, such as replacing the disc-type injector with a shooting-type system to further increase pellet velocity and repetition rates. Looking ahead, this technology has the potential to revolutionize the energy sector by providing a reliable source of clean, virtually limitless power. The integration of automated tracking and precise laser pointing will be essential in achieving the next milestones in fusion energy research. In conclusion, the horizontal homing laser system demonstrated by Agatsuma and his team is a key technological development that brings us closer to the commercialization of fusion energy. Their successful demonstration of pellet tracking and laser alignment at 10 Hz is a significant step forward in the journey toward sustainable fusion reactors. Thank you for watching. If you found this video informative, please like, share, and subscribe for more content on cutting-edge scientific research. And feel free to leave any questions in the comments below.